So today the agenda, we'll start with some quick overview of what has happened in IHE radiology in the last many years, and what are we going to do in the new decade. And then we'll talk about some of the new profiles that are AI related that we're developing this year. We'll go through some background, why those are important, as well as some overview of the two profiles that we're working on. And then we'll talk about some next steps. What are the activities that are coming up that you may be interested, and then we have some Q&A session. So for IHE radiology, like entering into a new decade, maybe let me talk about what happened in the last few years. And I want to call it like a high frequency healthcare enterprise. What do I mean by that is if we look at the major changes coming in the healthcare enterprise, we see that changes are happen, major theme changes much more frequently than it used to. So for example, back in the 1990s, we have PACS deployment. We started with digital PACS deployment. And then in the mid 2000, like we have VNAs. We started to see like enterprise deployment and consolidation of some technologies to the enterprise level. And 2015, we start seeing the theme of like enterprise imaging, and it's still very active going on, lots of activities there. And a couple of years later, we see activities on the AI, and it is very active today. So we see that activities going on with new major theme coming up in a much more high frequency fashion. And along the way, we also have continuous advance in imaging. So what has IHE radiology done in order to address this high frequency changes? So if we look at what happened, IHE has been pushing the boundaries of interoperabilities, trying to catch what is on the horizon. So when we started with the PACS deployment, there are many different systems they try to integrate. And I actually see the need for interoperability. So in the late 1990s, like, and then early 2000, we started to establish interoperability profiles, working on actors, transactions, and interoperability profiles. So we started with some of our core profiles like schedule workflow, PIR, KIN, and then later on in the 2007, like we started to expand from a departmental workflow to an enterprise workflow. For example, we're working on XDSI, and then we have IOCM, or imaging object change management, to address some of the synchronization issues when people start deploying VNA. That is a pain point at that time. And also, we also started to update some of our existing technologies like schedule workflow. We started to work on a refresh of the technology stack with schedule workflow.b. And I'm happy to mention that like schedule workflow.b is being final text this year, finally. And at the same time, we also catch some of the new technologies like DICOM Web or FIRE. We started developing some new profiles that make use of those new technologies like the web-based image capture and web-based image access. Those profiles leverage the DICOM Web to interface with some of the newer system and use some of the newer technologies that complement the existing workflow. At the same time, we also keep an eye on some of the regulatory requirements. So for example, CDS, it becomes important. So we also create a profile to standardize on the content to communicate clinical decision support information. And in the last couple of years, we developed a profile called the encounter-based imaging workflow that address some of the need in enterprise imaging. Along this way, we also address some advanced imaging need, like for example, the mammo, the digital breast tomosynthesis, and also radiation dose monitoring. So as you see, like in IHE, we're trying to push the boundary of interoperability and catching up on all the major themes going on along the way. So the next question is, what's going to happen next? And as I mentioned earlier, AI is definitely a big thing coming up. So we want to make sure we set the good foundation for AI to have a good interoperable way that can easily integrate into the radiology workflow. So the next speaker, Dr. Prevdello, will talk about why AI is important in radiology, and then we'll follow up with Kevin and Chris, who are the lead author of the two profiles. They'll give you a quick overview of the two profiles that IHE Radiology developed, and then we'll finish up with Terry that talk about some of the next step, what are the activities going up in radiology related to the AI domain. So let's get started.
Hello, everybody. My name is Luciano Prevdello. I'm from Ohio State University, and thank you very much for the invitation to speak here with you this morning / evening, depending on where you are in the world. What I thought would be interesting to talk about here is to talk a little bit about artificial intelligence and also how it's applied in the clinical setting and some of the integration needs that we all have for this to work properly. I would like to acknowledge the people in the OSU AI lab, composed by physicians, engineers, medical physicists, technologists, and interns. Some of the algorithms I'll show were developed in-house, others by vendors. And here's the outline for my part of the talk. Essentially, give you some examples of clinical applications of AI in radiology and their integration needs. I'll focus on a few examples, triage, image interpretation, especially detection and quantification, some additional back-end and front-end integration needs, and a summary at the end. So to start off, so I'll use this image lifecycle just to situate where we are in that algorithm application. So in a typical scenario in the clinical setting, we have patients, getting an image request, and then we protocol. That image is acquired by our technologists, and then we interpret, and then treatment decisions are made, and the patient is reassessed based on the imaging findings. What I would like to focus for the talk are two specific points of this imaging life cycle. First, the triage. And triage is so important, especially in academic settings, that we have so many sick patients, very, quaternary or tertiary centers dealing with very complex diseases. And in that setting, it's very difficult to prioritize what imaging studies to focus first, because, for example, 40% of our inpatient orders are considered stats. So we have to have high priority to a large number of cases. So what we try to do with using artificial intelligence is to see if we could prioritize the studies not based on the time that they were ordered, but based on the image findings, leveraging deep learning, which is a form of artificial intelligence. So we included in that algorithm several examples of critical findings, including hydrocephalus, hemorrhage, mass effect, and provided also examples of normal. We developed an algorithm leveraging the deep learning algorithm with an ROC of 0.91 to detect those intracranial hemorrhages, mass effect, and hydrocephalus. For stroke, it was difficult to add into the whole mix because these are very subtle findings, and neuroradiologists performed about at a 0.87 based on previous publications. We were able to get to a 0.81 performance. And the idea, you can imagine, is to use these technologies to make our scanners intelligent or apply them to prioritize based on those predictive probabilities, prioritize these scans or notify the radiologist that there's a critical finding sitting there for us to review. We published this on Radiology. You can take a look at that if you want to know more. But here's the application of that idea. And so this is a non-prioritized work list. And I don't know if you can see, the fonts are very small, but there is a very, there's a hemorrhage in the bottom of the list. Typically, we go from top to bottom based on the acquisition, but then leveraging these types of technologies, we wanted to see whether this hemorrhage here that is very important to treat first because it's a subdural hematoma with a mass effect midline shift, what we call it, and very ominous finding. There are also critical findings here in these cases, including hydrocephalus here, hemorrhage, the smaller hemorrhage here on the overlying the right frontal lobe, and others that are chronic findings or normal cases. So based on that assessment from the initial AI, we can then reprioritize that work list, and this is the lighting, the little light bulb here means that the AI was able to adjudicate, review these findings to detect the critical findings and sort out the work list more appropriately. So we're helping us deal with the most acute and more important findings, image prioritization. Another utilization of that type of technology is on image interpretation, and I'll start with lesion detection. We developed this algorithm to detect intracranial metastasis based on MRI, T1 weighted image with contrast. So initially, we segmented all these lesions using a tool that we developed in-house. As you can see here, the idea behind this slide is to just emphasize the fact that these metastases can be very, very small in size, and that's the beauty of AI, because if you miss one of these lesions, it has very profound clinical implications to the patient. This is a sagittal view showing the distribution of all the metastatic disease to the brain in all our cohort of hundreds and hundreds of patients that we segmented all these lesions to create the algorithm. And here's the performance of the algorithm. So small brain metastasis detection, and here's some examples of how small they can be. So you can imagine how difficult it is to go through these scans. Typically have about 300 images. So it's difficult to evaluate them, clinically, and it's also possible to miss these lesions because, as you can see, they're very small. The performance of the algorithm we were able to develop reached with a sensitivity of 90%. We have this is a false positive cases, about 10 false positive cases for that sensitivity. So as you can see, not perfect, but also from my standpoint, I prefer to go through these 10 false positives and make sure that I'm not missing any and not negatively impacting on patient care. So there is a real assistance and an importance to use these tools clinically. This is our, we integrated the tool into our current packs using DICOM standards. We can toggle them on and off. Here is how you would toggle them on and off based on those DICOM standards to enable the AI adjudication and review. But also in alignment with what the FDA has proposed, which is not only you not only need to validate your models, but once deployed, the model also needs to be monitored to make sure that it's still performing the way that it was designed to perform, and that constant monitoring is really important. From an AI deployment standpoint, we developed this tool that allows the neuroradiologist to review the AI-based annotation. So here's a metastatic disease. This one, it was a false positive. So we can go there, right-click, and delete that measurement. Once you do that, there's a feedback loop to the algorithm, so an inference adjudication by the radiologist. So we're constantly teaching the algorithm to learn more about these cases. So we're adding new cases and trying to make it more generalizable. As far as quantification, this is a tool that we did not develop, but we have implemented here, just to give you a sense of how complex this can be. And this is based on an MRI T1 without contrast. You can evaluate, segment all the brain parenchyma, several of the lesions, and then report the volume of each one, try to assess whether there is an asymmetry between the structures, whether that falls outside of the normality for that patient's age. And as you can see based on this slide, there's a tsunami of data that AI can produce, and we need to have the right integrations to be able to consume that data. And obviously in this case, the integration is not so much on the ability to review, but we need to consume that data in our reports in a structured format. So there are multiple areas where integration is so key. And I provided only a few examples of integration points in the clinical setting that AI has a special need. In addition to those, there's also the back-end and a few other front-end integration needs as far as the AI goes. Because the acquisition can be from multiple sources, the integration and connection with can happen with multiple different applications. There's a need of that coordination between all these systems. One thing that is very difficult when you start implementing these tools in a clinical setting is that each vendor has their own way and infrastructure requirements to put these tools together. And what we end up seeing is a number of machines or servers needed to be implemented in order to address these needs. And that's obviously a back-end, infrastructure integration need that we have in order to decrease the number of servers required. There's a lot of activity going on in making these tools a little bit more plug and play, such as we see with these big IT vendors, Google and Apple's, to make it more streamlined. Certainly an area of interest and need. The other part of the integration, which is more on the front end, this is the ideal scenario. The same place where I'm reviewing the images, I can click a button or right click and then get to the AI results right there. A little bit less of a integration would be to have a link or a button to launch a separate application. If we go to another substandard format would be to launch an application and have to log into to that application, username and password. And then even worse than that would be to have a completely separate application in another room that you have to walk and in a dedicated environment that is completely detached from the clinical workflow. So as you can see, as you go from the left to right, there is not only a decreased integration, but also a decreased utility. The likelihood that your radiologist is going to use that application will certainly decrease, the less integrated to the clinical environment that is. And then, as I mentioned before, there's also the importance of collecting that radiologist feedback. So the feedback loop that we try to create and monitor not only the adoption of these tools, but a continuous monitoring of that algorithm performance is also key. So those are some of the important points. I think it's with that, you can see that AI is a pretty powerful tool. It has arrived to really improve workflow and enhance patient care. But we need to pay attention to that integration, which will be key in the adoption and the clinical utility of these tools. And also important to pay attention not only to the front-end integration, but also to the back end. So with that, I hope I was able to give like a very high-level overview of some of the important points as far as the integration, interoperability and the needs of AI in the clinical setting. Thank you very much.
Thank you. So our next speaker is Kevin. Kevin, if you're speaking, we cannot hear you yet.
Mute again. Is that better?
Yep, we can hear you now. Thank you.
Okay, double muted, I guess. So thanks, Dr. Prividello. That sort of establishes the space that IHE Radiology was looking into as we started on our first pair of profiles for the IA space. It's an enormous space, clearly. There's a lot that could be done, and so this particular profile is focused on the area of AI results that are being provided to the radiologist or the cardiologist or imaging clinician in the context of that image interpretation box that you saw in the previous presentation. And so, a lot of you are in the space and you'll be familiar. I'm sure some of you participated in SIM's pneumothorax challenge this past year. And so basic idea, you've got an AI algorithm. It's generating some sort of a radiological finding or cue or piece of information. And that algorithm then needs to find a way, as Luciano was showing, of how does it then display into the radiology reading workstation of whoever it is they're working with. Well, then they'll of course have another site who has a different display system, and many more sites who have many other different types of display systems, and they'll work their way through trying to get each of those integrated. There are many algorithms out there doing things, diabetic retinopathy, skin lesions, wrist fractures, lung nodules. You get the picture. This is, an initial sampling, and we all know there are just going to be more and more of these coming out. And of course, each of those is going to be faced with the same problem of then integrating with all of these different environments and these different display systems. And you could easily go down the bad path of that room full of servers that Luciano was showing, and having to deal with all of these separately. This is, a classic many-to-many problem, which is basically the reason that we develop standards. The developers of AI algorithms have better things to do with their time than try and figure out how to integrate with a dozen different display systems. And the display developers have better things to do with their time than do one-by-one integrations with 100 different AI algorithms. So the point here is let's try and standardize the formats, and that's the essence of what this profile is pushing for. So the target systems are these AI analysis software, whether they're standalone packages, whether they're integrated into a platform, however it is that they're being deployed, you've got the systems that generate these AI results. PACS, as usual, sits in the middle and stores the imaging study. Today, they've got the regular images, various clinical application results, things that are analogous to what the AIs are doing, but done by humans or done by more conventional software. And then you've got the image displays. And so our goal here is we want to standardize the storage and standardize the display. As you'll see, we're not quite standardizing the display, but we want to set some baseline behaviors so that you get at least a basic level of functionality for any new algorithm that you're plugging in. So the approach to this will to look at the collection of AI results that are being generated and do something similar to what we did with presentation states, which is to try and break things down into a set of result primitives, which we'll see in a coming slide. And then for each of those primitives, for the AI analysis software, come up with encoding requirements on how each of those will predictably and consistently be encoded. And then on the display side, what the baseline display requirements are for each of those primitives, so that an AI analysis software, as long as they can break their particular findings into a collection of these primitives, they can be confident that the various display systems will be able to do something reasonable with the results they're sending without one-on-one integration work. So the basic use case for this is, as you've it's not very complicated. Evidence creator obtains images and creates results and stores out those results in a standard format. The image display during the review process can then retrieve those and present them to the user. The second use case, which is also important, and we show sort of DIMSY conventional DICOM transactions on the left and DICOM web on the right. Those can swap. Basically, the profile points to how to stow these both using DICOM web and the more traditional DICOM. But the key point on the left is that we have other consumers beyond the image display. So we want systems to be able to go in, as we saw in the previous presentation, as you're generating the report, you want to be able to extract measurements, proposed findings and classifications directly out of the AI finding and be able to put those into the report for the radiologist to either keep or delete. You want to be able to pull this information into clinical databases. Cardiology is an area where they do a lot of databasing of results to track things over time. Oncology, as you saw with some of the brain segmentations. So again, the results need to be machine readable. And then thirdly, things like driving clinical decision support, that having these in a machine readable form, and you could argue really that work list prioritization is simply one form of clinical decision support. So it's important that all this be machine readable. So the result primitives that we came up with, first was essentially qualitative findings. Things like pneumothorax is present or the breast composition is extremely dense. Measurements are clearly going to be part of the picture. You'll have a measurement concept for what it is that was measured and what the measurement values were, and there can be large numbers of those. Locations, as you again saw in the previous presentation, may have detected a blood clot. It's at these coordinates. Segmentation, so it's not just a location, but what are the contours of the thing that was found. There's a lung nodule. Here is a segmentation of the lung nodule surface. Maybe you're feeding that into estimations of growth. Parametric maps have shown up a lot. So one of the challenges that AI faces is building up a degree of confidence and trust with the radiologists and the imaging clinicians that are using it. And one of the key things that's been used in a number of these is what's called a saliency map, essentially a heat map, so that if the system is outputting that pneumothorax is present, it can give some indication of what parts of the image were key in triggering that finding. And that helps the radiologist understand what's driving this finding and whether or not they agree with the finding or not. Tracking IDs. So some of this stuff is for things that are consistent over time, that if you have a particular tumor and you're remeasuring it at multiple locations, sometimes that's the output of the AI. It does automatically matches up tumors over time, or it's using that to correlate its measurements with prior measurements. There are image references scattered through all of this. So for example, locations are frequently relative to a particular image. And sometimes the output itself is simply an image reference. So the AI, tell the AI, give me the best view of the brain hemorrhage or whatever characteristic it is you're looking for. So all of these were built up based on a catalog that we had. DICOM Working Group 23 has been working on in this area. The ACR DSI has been doing an extensive set of work on use cases and how all this can be applied. So a lot of crosstalk between those groups. So when it came to the encodings, we want these to be machine readable. We have structures within DICOM SR, specifically the TID 1500 template, which is a basic measurement structure that allows for both quantitative and qualitative findings. It typically, all of SRs are able then to incorporate spatial coordinates and spatial 3D coordinates, so in both image space and three-dimensional space. Segmentations would go into one of two ways. They can either go in as a segmentation object, which is a volumetric classification of pixels or voxels, or if they can go in as contouring, so slice by slice contours within TID 1500. The parametric maps that we're using for the saliency maps is a relatively new DICOM IOD that allows for floating point images. The tracking IDs are, again, a built-in feature, as is the image references. So finally, we get to the display behaviors. So, the question is, how is a display become, AI ready without having to go through and do customizations and, custom display behaviors for each AI model, which would be untractable given the number of models that are coming out. So what we've done is we've established a baseline of display capabilities. And so the idea here is we're not restricting displays from doing more, and we fully expect this will be a really interesting area of product innovation, and there'll be a lot of creative work that's put in there, but you want to have a fallback. You want to make sure that in the absence of something that they've figured out for each of these, that there's some basic levels of display, which is what we typically find with even how they display images today. So additional or alternate functions may be present, they can be invoked or configured, but you have to be able to do a certain set of baseline display capabilities. As examples, if you've done display measurements on an image, then those should be visualizable in the context of the image where they were measured. If you've come up with locations or CAD marks, again, you need to be able to show those on a corresponding image. You need to be able to present the segments and volumes. You need to be able to put up the labels for what those different segments are and what they represent. For the saliency maps, you have to be able to do fusion to fuse those onto an underlying image. A heat map floating in space really doesn't communicate much to the radiologist. If you fuse it onto the chest x-ray, okay, now they can see the correlation between the anatomy and the image itself and what's being highlighted. Associating multiple results by the tracking ID, so that the displays have to be aware of the tracking IDs and be able to navigate those, etc. And so there's more than will fit on a slide, but that gives you a bit of a feeling of what the requirements look like. So to see the rest of the requirements, the document has finished going through public comment. We finished doing all of the resolutions, and with luck, it will be published by middle of July. So it's off to the library group to make sure it's formatted properly and in good shape. Here's a quick navigation. If you go off to the IHE website, through resources, technical framework, and radiology, down under supplements for trial implementation, you'll be able to see it there. And thanks go out to all of the people who contributed to this profile. There's a lot of people who work very hard in the committee, And we also had loads of good input, both before we started working on it and over 400 comments during the public comment period. So thanks to all who've been contributing and helping pull this together. If you're new to IHE profiles, we're also playing around in this one. There's a very short how to read this document at the beginning of the profile. Profiles they contain chunks of stuff that's kind of boring boilerplate that if you know, you can skip over. So the how to read will hopefully point you to things depending on your what it is you're using the profile for that are hopefully of interest to you. So with that, thanks. And I think, Kinson, I guess we hand over to Chris.
Yep, thank you, Kevin. So our next speaker is Chris Linda. So Chris,
yes, I am here, and
can take the presenter role.
And I believe I'm sharing my screen.
Thank you, Chris.
You're welcome. Okay, so thank you for being here and listening to our presentations today. What I'll be talking to you about is the AI workflow integration profile. This is a new profile for this year, and it primarily focuses on integrating AI, clinical imaging workflow with AI. So in your normal environment, we're now seeing the emergence of many AI models, all of them having their own interfaces, how to launch them, how to control them. And certainly you don't want to go to a box in the back room that you have to go and log into and get it working. Those are the things you don't want to be doing. So this profile is targeted to really focus on taking these individual AI models, essentially providing a method of management, through orchestration, and being accessible through common interfaces, independent of where you are in the workflow. So the fundamental requirement is I need consult by an AI model. I want to know what they think. So it could be in any part of the process. It could be protocol, scheduling, acquisition, reading, interpretation, reading workflow management, all sorts of things. So that's what drove us to come up with this profile, focusing on the use cases to request, manage, and perform AI inference on the digital images. Very basic fundamental request. What kind of inference is desired? If you know, maybe all you have is, hey, I've got this CT, I want you to look at it. CT study, I want you to look at it. Maybe you can do it, maybe you won't. But keep it very broad, keep it very specific. You want to tell in the request, you want to say where the images are located, and non-clinical images data is located, and where do you want the destination of the results to be. Very basic and fundamental. It's all based on DICOM UPS-RS, which is a RESTful service, and it's very, very easy to implement. We've also included, because what we're finding in the AI models today, that they may actually find some results which would need attention in the workflow. So in this process, we've included the ability to notify the reading workflow manager that there may be a condition that needs to be addressed. Three major actors is the task requester, who creates the inference request, the task manager, who assigns the inference request, and the task performer, the one who performs the inference request. As part of that, though, you've got to have, there are a few other minor actors that we do have to bring in. Where are they going to get those images? Image manager. Let's provide as much flexibility with reporting the status update of the worklist priority as much as possible. So rather than say, this is the role of the task requester, or this is the role of the task manager. We've made a separate actor for that role of reporting the status update work priority. And certainly, who's managing that worrying worklist is the one who gets that update. Getting down to the nitty-gritty details. The task requester, they're the ones that create it. We talked about that. Essentially, gives the inputs, locations of the input information, and where the results are to be posted. As an option, we've built in an option in the image manager. Essentially, image manager has the ability to, if they do instance availability notification, the requester can receive that, and that could be a trigger for that requester, independent of where it is. It could be for a group of the task manager. It could be an independent. It could be grouped as there is for that matter. It doesn't matter where it is, but we've added new requirements on the image manager though to do the instance availability notification. In IHE world, it has been triggered off of a MPPS from the acquisition modality. Well, at this point, what happens if you don't get an MPPS from an acquisition modality? Well, you're going to have to make that happen regardless, and that's all part of the profile. There's also another actor which I haven't really talked about too much. Is the watcher actor. Watcher actors don't give, well, in itself, if you look up the upper right-hand corner, you see the task requester. Well, all he does is create a work item. Well, how is it supposed to know what the status is? Well, you're going to bring in the watcher actor. And that way, it'll receive notifications of when it's scheduled, when it's claimed, and when it's completed. This is great for, for the work list, work list managers. It's great for the packs to know, and for other systems to know precisely what is the status. Well, I've sent these things off. When's it done? That's how you'll find out. And certainly, who can be a task requester? Literally any system can be a task requester. Acquisition modalities. We've got workflow, that critical care workflow that they're working on, and they need to get the results. That technologist needs to get the results. Well, use the AI inferencing service to get it, or they just the acquisition modality just wants to get some advice on better image quality. Yes, you can do those things. Task manager, they're the actor that actually makes it all happen. They receive the request, they assign the inference, and they manage the work item. Task manager, one of the requirements that they really need is they have to know the capabilities of all their task performers. That's how they do the assignments. Using the UPS model, we try to provide as much flexibility for the task performer, the one who's performing the inference, for various types of workflow. And it's getting down to nitty-gritty details. You can do the pull workflow, a trigger pull workflow, or a push workflow. All three models are supported, and it really is up to the task performer to determine which workflow model that they would want to perform. And finally, I do want to put in about the task performer. You can also be a proxy as a task performer, an AI model proxy, where you would be, essentially creating your own workflow, within your proxy platform. The proxy platform, this will enable more container-based integration with other AI models. So it's something to look at, something to be of concern. And finally, the last section would be discussing reading workflow priority. In the typical process flow, you'll get an HL7 or OM or ONI message being sent off to whoever is doing the reading worklist to convey the procedure status. Give them, if an AI model finds something that's somewhat important, you need a method of conveying that information. Not necessarily that the receiving system will act upon it, but you have a method of providing those, presence, those findings, presence of a condition, to whoever's managing the workflow. Reusing the IHE Rad 13 procedure update message is what we are using to convey the status change. And of course, how to act on the information is up to the system managing workflows. It just gives you a little glimpse at of what's used for the reading workflow priority. Obviously, you want to study instance UID to really tie it back to the study that you're reporting on. You've got some of the key factors here, the OBX8, the abnormality flag. If you've got something that's abnormal you want to talk about. We've also added the critical findings category as well. So that's part of the what's reported, because even if you've got there are times that you would provide abnormality flag. And it may not only be abnormal, but it is critically abnormal, so it needs to be processed. So that's what the reading worklist priority looks like. The profile is, viewing its final stages of being published, and should be available shortly for actual implementation as actual usage. As there's certainly the trial implementation draft that's available, while the final cleaned up version is being put out there for general distribution. And with that, I will hand the presentation back over to it goes to Terry next.
Yep. Thanks, Chris.
You're welcome.
Terry.
Hi, everyone.
Did you get the presenter role? Oh.
So my name is Terry Sippel-Schmidt. I am with the Marquette University, and I'm hoping that we will start presenting any minute. There we go. I also have a contract with RSNA, which explains one of my next slides. So just to kind of reiterate what we've heard so far today, we heard Luciano talking about how important artificial intelligence is and all the different applications, with him focusing on triaging or triaging the work list, detection, and then quantification. And then we heard Kevin talking about how to submit these results from these artificial intelligence algorithms. And then we heard Chris talking about how important it is to integrate all the workflow. And so on that note, to kind of summarize these things, the things that I wanted to mention was that these two new profiles, the AI results, as well as the AI workflow and imaging, are coming out hopefully mid-July, so soon, in a week or two, and that you need to read these profiles in detail. You need to start to implement these profiles. And as you implement the profiles, if you run into issues, there's ways to submit a change request or a change proposal within IHE, which any of the speakers would be glad to help you with. And that's part of the IHE process, is learning as we go. And to that end, we have something called an IHE Connect-a-thon. Now, I would like to think that most of the people on the call are familiar with them, but if not, it's usually all bets are off now, but it's usually an in-person event with hundreds of people where we get together with hundreds of engineers and hundreds of systems, and we connect them all together over the course of a week. And we run through some independently monitored test cases. And it really illustrates all the different, I don't want to say problems that the different systems have, but it gives people the opportunity to work together in almost an academic, but non-controversial, non-competitive setting, and to be able to work things out. The North American Connectathon is held in January in Cleveland. The European Connectathon is usually held in April. The location for 2021 is to be decided. And there's a lot more information about the Connectathons on the IHE, excuse me, webpage. There's also the IHE, I'm sorry, SIM, the Society of Imaging and Informatics Hackathon. And it primarily focuses on DICOM web services, I'm sorry, FIRE, DICOM web services, and then SOL, which stands for Standardized Operational Log of Events, which is also an IHE profile. And that can be joined either as virtual, as it was this year, or on location in Portland, Oregon in June of 2021. And that's just another opportunity for you to work with other vendors or academic partners and test out your implementations and learn a lot. One of the other things I want to mention, however, was that in addition to all of the workflow and the transport, one of the things that's really important is all of the data and the codes that are coming out of these AI algorithms. So Kevin mentioned both quantitative and qualitative results. I'm a big fan of code systems and of actually having codes which indicate not just abnormal, but the types of abnormal codes, as Dr. Prevatello was discussing. There's quite a few different RSNA as well as ACR initiatives which are covering all the different kinds of codes and the things that come up. For example, the ACR assessment categories, which can have, for example, the lung RADS, which is a CT screening, cancer screening protocol. And it gives you very specific codes with very clear definitions of exactly what the radiologist saw. And that's why they're reporting it as a certain code system. There's a lot of information out there, and this can be used in conjunction with the two profiles which you just heard about. And on that note, and this is a world unto itself, but I just want to mention to everyone that it's there and it's worth taking some time to go and review. On that note, I'm going to turn it back to Kinzen for questions.
All right, thanks for all the speakers today. So now we're opening up for any questions. So I saw one in the chat from Amen. Are there any other IHE resources, checklists, or conformance statement available which can be used by imaging service providers to evaluate their PACS risk system and or vendors to evaluate their AI algorithms from IHE AI or RAD profile standpoint? So every vendors that implement any of the IHE profiles, radiology or other IHE domains, they will publish something called integration statement. So it's usually is a 1 page, 2 page, very simple document that lists all the profiles that they support, which actor in those profiles that they support, as well as any options that the actor support. So that gives you a good overview of what are the capabilities that system has, and then when you read the profile for the requirements of that particular actor, then you get a sense of what are the supported capabilities of that particular system.
Yeah, and can I jump in?
Kevin.
Yeah, and so as Kinson says, each vendor publishes an IHE conformance statement for their products. Since these two profiles are, the ink is still wet, you won't find that on any integration statements today, but you can Google for them. There's also an IHE, if you go to product-registry.ihe.net, some vendors post them there. Mostly we post them on our own websites, so Google will help you find them. And then there's connectathon-results.ihe.net. As Terry was describing, everyone who passes Connectathon for a profile gets listed. We don't pass the failures because, you know, maybe they're having a bad day, but you know, so if they do pass, they get recorded. So that's a second place you can look. And then on the DICOM side, because a lot of this is built on the DICOM conformance statement will have clues, I guess. So you can look for the underlying features, like in the case of AI results, do they support, if it's an AI algorithm and they support segmentation, DICOM segmentation objects, likely they are outputting their segmentations using those objects. If they support DICOM SR and they list TID 1500, so it's tidier and easier for you to go look at the IHE integration statement. But until those are out, there's a few other places you can get some clues.
Thank you, Kevin.
Mm-hmm.
Any other questions?
Well, I see Terry put up a question, and her question basically does AI, or actually AIW has a method for accepting or rejecting the AI results, and the way it does it, and the way it provides that is basically we have a two-step workflow process that allows you to review the results before they are actually they are actually stored to their final destination.
Yeah, and I bet Terry's queuing it up partly for Luciano. So as people saw in Luciano's initial presentation, at the time of review, the radiologist may click and say, "Oh, that was a false positive," and that's really useful information for retraining the algorithms. That's one of the really interesting problems that we said we'll get to maybe next year. So the quick answer is if it's an edit, or if it, you know, that there is in DICOM mechanisms for approving data, and you could certainly edit it and store your new one, but we haven't found the mechanisms in a nice feedback workflow, because obviously we'd then like to say, okay, now how do you get that back to a data pool that you can use for retraining or for some of these discrepancy reviews and things. So the quick answer is, yeah, there are mechanisms in DICOM you could kind of use, but it's a tricky space, and we want to do it properly. So that may be a proposal for next cycle.
Yeah, like I said, we put that in the AIW profile as a two-step process so that you don't store it. But there is, as Kevin mentioned, there is no. We did profile the feedback mechanism in the AIW profile. Other things that we didn't do this year is interactive as well. That we're holding off something like the interactive AI, which would be similar to that type of a model.
And what Chris is describing is if you crack open the AI workflow profile, there's a scenario called verification, which, as Chris was describing, when the result is generated before it's released into the hospital data systems where people can look at it. Some groups describe that they would like the results pre-vetted. And so Chris wrote up a section on how to set up a second sort of review task following generation task, which creates storage of the data. So if you're doing pre-reviews, it's true, those are covered in the AI workflow profile.
Yep.
Thank you. Any other questions?
I just want to take 1 minute, Kinson, to promote the RSNA 2020 imaging AI in practice demonstration. It'll obviously be virtual this year, but our experience this year is with taking almost 30 different products and trying to do this integration without international standards being in place yet. It's been interesting. It's been frustrating. It's been time consuming. And as of right now, it's not working very well. However, next year we plan to continue the imaging AI in practice demonstration, and God willing that we're actually on site in 2021. But the intent is that we will be much more closely following the international standards, including the 2 profiles that we just reviewed, as well as IHE SOL, which stands for Standardized Operational Log of Events. And SOL is how we will be able to monitor what's going on throughout the department and in turn justify to the administration an ROI to be able to invest in these AI algorithms. And so that's a really key component to all this as well.
Thank you, Terry.
For anyone who's got access to the chat, Aman kindly typed in the 2 links if you want to find out about products and companies and the IHE profile support.
Okay. So we're on top of the schedule time right now. So one last question, if there's any. If not, then thank you very much. Thank you for everyone that attend, and thank you also for all the speakers preparing the presentations. The presentations and the recordings will be available in the IHE website later. Thank you once again, and have a good day, everyone.
Thanks, everybody. Bye-bye.
Bye.